Welcome back, Design Junkies, to Mechanical Engineering Made Simple. If you enjoy the podcast, show your support with a like, a follow, or a comment.
Absolutely.
Today, we are inviting you into a very special masterclass. It's a deep dive into the hidden rules that govern, well, almost everything around you.
Yeah, it really is everything.
And looking at our sources for today, we've compiled a massive stack of historical engineering texts, fluid dynamics research papers, and real-world case studies. But our mission today isn't just to read you some math.
No, definitely not.
Our mission is to build a mental toolkit. We want to permanently change how you look at the physical world. And I want to start by painting a picture for you.
Go for it.
Okay, imagine the massive steel propeller of a modern ocean freighter.
Right, those things are huge.
Massive. It's a solid piece of meticulously cast metal. It weighs tons, and it's designed to push millions of pounds of cargo across the Pacific Ocean.
Yeah.
But when shipbuilders pull these propellers out of the water after a few years, they often find the solid steel looks like it's been eaten away by acid.
It's completely destroyed. Yeah.
It's pitted, scarred, ruined. You might think it's, I don't know, chemical rust. Or maybe it hit some rocks on the ocean floor.
Which would be a good guess.
Right. But it's neither. That solid steel was destroyed by microscopic bubbles of water.
What's fascinating here is that the sheer destructive power of a collapsing water bubble is one of the most extreme, mind-bending phenomena in the physical world.
It really is.
And the craziest part is that the physics dictating how those microscopic bubbles destroy steel,
Yeah.
they are the exact same physics dictating how a curveball drops over home plate, or how the Romans designed aqueducts thousands of years ago,
Oh, wow.
or even just why a garden hose behaves the way it does when you put your thumb over it.
I mean, fluids seem inherently chaotic, right? They're constantly shifting, swirling, deforming.
Exactly. They look like pure chaos. But beneath that apparent chaos is a shockingly elegant set of rules.
And we are going to map out exactly why fluids behave the way they do today. We aren't just going to list off intimidating mathematical formulas. Yeah, we're going to unpack the underlying logic. So here's the syllabus for our deep dive today. We've got 4 main modules.
Module 1.
Right, Module 1. We're going to start by looking at an impossible perfect universe where fluids have no friction, just to understand the foundational rules of energy.
The ideal world.
Yep. Then, Module 2, we're going to drag that pristine math into the messy, sticky reality of our world to understand turbulence.
Where things get complicated.
Very complicated.
Yeah.
From there, Module 3, we will rip the roof off our pipes and look at how gravity drives open rivers.
Open channel flow.
Exactly. And finally, Module 4, we'll flip the camera entirely. We'll look at what happens when solid objects like airplanes, golf balls, and those ship propellers try to force their way through the fluid.
You know, the path we are taking today actually mirrors the historical journey of human understanding.
Oh, really? How so?
Well, the earliest physicists had to pretend fluids were perfect and frictionless. They had to, just to get their equations to work.
Ah, I see.
But nature, as we know, is never perfectly frictionless.
Right, far from it.
The monumental breakthroughs that gave us modern aviation, advanced plumbing, and global shipping, they all came from finally embracing the friction and understanding the chaos.
I love that. Okay, so let's start in that perfect, ideal world. Because before we can possibly understand the complex, swirling, three-dimensional chaos of a hurricane.
Or the chaotic wake behind a semi-truck on the highway.
Right, exactly. We have to master the rules of a simplified universe first. So picture a one-dimensional universe where we only look at the average straight-line velocity of a fluid moving through a pipe.
Okay, so to do this, we imagine a theoretical fluid. It doesn't stick to the walls of the pipe, it doesn't heat up, and crucially, it doesn't lose a single drop of energy to friction.
It's perfectly smooth.
Perfectly smooth. Physicists call this an ideal or inviscid fluid.
Viscid, got it.
And in this incredibly simplified sandbox, the fluid is ruled by a few absolute, unbreakable laws of physics.
Okay, lay the first one on me.
The first of these is the conservation of mass. In the realm of fluid mechanics, this is mathematically expressed as the continuity equation.
Okay, the continuity equation sounds like something out of a graduate-level textbook.
It does sound intimidating, yeah.
But the underlying concept from our sources is beautifully simple. It just means what goes in must come out.
Exactly.
If you have a solid steel pipe and you aren't adding any extra fluid through a side valve,
And the pipe hasn't sprung any leaks.
right, no leaks, then the absolute mass of the fluid flowing into the entrance has to equal the mass flowing out of the exit in that exact same amount of time. You can't magically create or destroy water inside the pipe.
Right. When you write that out mathematically, you say that the mass flow rate is constant everywhere in the system.
Okay, so how do we calculate that?
The mass flow rate is calculated by multiplying three specific variables together:
Which are?
the density of the fluid, the cross-sectional area of the pipe, and the mean velocity of the flow. So, density 1 times area 1 times velocity 1 at the entrance must perfectly equal density 2 times area 2 times velocity 2 at the exit.
I follow you. But let's bring this down to earth and talk about liquid water, because that allows us to cheat the math a little bit, right?
It does, yes.
Because water is, for all practical everyday purposes, an incompressible fluid.
Right. It doesn't squish.
Yeah, you can put it in a hydraulic press and squeeze it with thousands of pounds of force, but its density isn't really going to change. A gallon of water is a gallon of water.
Exactly.
So if the density of the entrance is the exact same as the density at the exit, we could just cross density out of the equation entirely, right?
That is the crucial simplification. Once you cross out density, you are left with something incredibly elegant.
Which is?
Area times velocity is a constant. Area 1 times velocity 1 equals area 2 times velocity 2.
Okay, and this mathematical statement, area times velocity is constant, is something I guarantee every single person listening has experienced intuitively.
Oh,
It's the classic backyard trick. You know, putting your thumb over the opening of the garden hose.
the perfect example.
Right. You're out in the yard, the hose is running, and the water is just sort of lazily spilling out onto the grass. The hose has a certain circular area, and the water has a certain lazy velocity.
Yeah.
But then you want to spray your friend who is standing 10 feet away.
As you do.
As you do.
Yeah.
So without even thinking about the physics, you clamp your thumb over half of the opening.
Think about what you are physically doing in that moment. You are dramatically reducing the cross-sectional area that the water has available to flow through.
Okay.
But remember the continuity equation. Area times velocity must remain constant,
Right.
because the spigot attached to your house is still pushing the exact same mass of water into the hose every single second.
The water has nowhere else to go.
Exactly. If you cut the area in half, the velocity has absolutely no choice but to double to maintain that mathematical balance. The area goes down, the velocity skyrockets, and suddenly you have a high-speed jet of water hitting your target.
I love this because my entire life, I thought I was increasing the pressure of the hose with my thumb. That's what it physically feels like when the water pushes back against your skin.
It does feel like that.
But I'm not changing the pressure from the city water line at all. I am just manually trading area for velocity.
Exactly.
I'm forcing the same amount of traffic through fewer lanes, so the cars have to speed up to get through.
That traffic analogy is spot on. And the idea of trading one property for another brings us to the second unbreakable rule of our ideal universe,
Which is?
the conservation of energy. In fluid dynamics, this concept was codified into what is arguably the most famous equation in the entire discipline.
Bernoulli's equation.
Bernoulli's equation.
Right, Daniel Bernoulli, an 18th century Swiss mathematician. He was actually the one who coined the term hydrodynamics in the 1730s.
He was brilliant.
He realized that for our perfect frictionless fluid, the total energy of a fluid particle traveling along a streamline remains perfectly constant.
And the genius of Bernoulli was identifying that this total energy is distributed across three distinct bank accounts, so to speak.
Bank accounts, I like that. What are they?
Well, a fluid particle has kinetic energy, which is the energy of its physical speed.
Okay, kinetic is speed.
It has potential energy, which is the energy of its physical height or elevation relative to gravity.
Potential is height. Got it.
And crucially, it has pressure energy.
Pressure energy. Okay, to make the relationship between potential and kinetic energy relatable for you guys listening, let's picture a roller coaster.
Oh, that's a great way to visualize it.
Right. When you are sitting in that little cart, slowly clanking your way up to the very top of the highest peak, you are depositing energy into your potential energy bank account.
You are building up height, storing gravity's potential to do work.
Exactly. At the very top, just before the drop, your potential energy is maxed out. But your kinetic energy, your speed, is basically zero.
And then you tip over the edge.
Right. As you plummet down the steel track, your height rapidly decreases, meaning your potential energy bank account is draining.
What the universe demands that energy be conserved. That energy doesn't vanish.
It is seamlessly transferred into your kinetic energy bank account. Your speed skyrockets.
Yeah.
At the very bottom of the hill, your potential energy is basically zero, but your kinetic energy is at its absolute maximum.
And assuming a frictionless track, The total sum of those two bank accounts is exactly the same at every single inch of the ride.
So fluids do the exact same thing. If water flows down a mountain stream, it trades the potential energy of the mountain's height for the kinetic energy of the rushing rapids.
They do.
Yeah.
But here is the piece of the puzzle that makes fluids completely different from a roller coaster cart.
Right, the third bank account.
Fluids have that third bank account, pressure. Bernoulli proved mathematically that the sum of kinetic energy, pressure energy, and potential energy remains constant.
Okay, so how do we isolate that pressure variable?
Let's remove gravity from the equation entirely. Imagine a perfectly horizontal pipe.
Okay, a flat pipe.
The potential energy never changes because the height never changes.
Right.
Now, the fluid is only trading energy back and forth between two accounts. Its speed and its internal pressure.
Okay, let's connect this back to our garden hose, or just a pipe that gets narrower in the middle.
Okay.
We know from the continuity equation that when the horizontal pipe gets narrower, the water has to speed up. Its kinetic energy goes up.
Yes.
But Bernoulli's law says the total energy cannot change. So if the kinetic energy bank account suddenly gets a huge deposit, the money has to be withdrawn from somewhere else.
It has to steal that energy from the pressure account.
Wait, so it steals from pressure?
Which leads to the most profound and, frankly, the most counterintuitive realization in basic fluid dynamics. What's fascinating here is that where the flow is fastest, the internal pressure is lowest.
That is wild.
If you force water through a narrow constriction, it speeds up, and its internal static pressure plummets.
That breaks my brain every time I think about it.
It's hard to grasp at first.
Because if I am in a wide hallway, and the hallway suddenly narrows into a tight corridor, and a crowd of people is forcing their way through, the pressure goes up, people are squeezed together, you feel crushed. Why does water do the exact opposite?
Well, the confusion comes from our human bias towards solids. We intuitively think of pressure as things being physically crammed together.
Yeah, exactly.
But in a fluid, pressure is created by the random microscopic bouncing of molecules against the walls of the pipe.
Bouncing molecules.
Imagine a swarm of angry bees inside a box.
Okay, angry bees.
They are bouncing off the walls furiously. That creates high pressure on the walls.
Makes sense.
But now, open one end of the box and blow a massive fan behind them. The bees are all swept forward at high speed.
Oh, I see where this is going.
Because they are now spending all their kinetic energy moving rapidly in one straight direction, they don't have the time or the lateral energy to bounce sideways against the walls anymore.
Wow.
The straight line speed increases, but the sideways pressure against the boundary dramatically decreases.
That is a brilliant way to visualize it. Directional speed steals from lateral bouncing. Fast-moving fluid equals lower pressure.
Exactly.
And this realization wasn't just some abstract chalkboard math that stayed in the university. It completely revolutionized engineering and measurement.
It really did.
There's this amazing historical anecdote from 1732 from our sources, right around the time Bernoulli was doing his work. It involves a French engineer named Henri de Pitot.
Ah, the invention of the Pitot tube. It's one of those rare moments in history where a complex theoretical physics problem is solved with startling simplicity.
So Pitot was standing on the banks of the River Seine in Paris. He was wrestling with a very practical problem. How do you accurately measure the velocity of flowing water in a massive river?
It's a tough problem.
You can throw a piece of wood in and time it, but that's wildly inaccurate. Pitot's thinking about this deep relationship between pressure and velocity.
Right?
Suddenly he has an epiphany. He grabs a simple piece of glass tubing, bends it into an L shape at a perfect 90-degree angle, and plunges it straight down into the river. He points the open, submerged end directly upstream into the oncoming current.
Think about the physics of what happens next. The rushing river water enters the open end of the glass tube.
Right.
But the tube is a dead end. The water has nowhere to go inside the glass.
Good.
So the tiny parcel of water just inside the mouth of the tube is forced to come to a complete and total stop. In fluid dynamics, we call this a stagnation point. The velocity drops to absolute zero.
And this is where Bernoulli's energy trading comes into play. If the kinetic energy drops from the speed of the river down to absolute zero, all of that forward energy must be instantly converted back into pressure energy.
Exactly right. This creates a localized microscopic zone of extreme high pressure at the mouth of the tube. We call this the stagnation pressure.
Stagnation pressure.
And this localized high pressure physically forces the column of water up the vertical part of the glass tube. It pushes the water up until the column inside the glass rises noticeably above the surface level of the river itself.
So the faster the river was flowing, the more kinetic energy it had to convert, and the higher the water column rose in the tube.
Precisely.
By simply measuring how many inches the water rose above the river's surface, Pitot could calculate the exact mathematical velocity of the current. He turned speed into a visible, measurable pillar of pressure.
It remains a stunningly elegant instrument. A Pitot tube simply compares two things. It compares the stagnation pressure, the total pressure where the flow stops dead inside the tube, against the static pressure of the normal, undisturbed river flowing around it. The difference between those two pressures is entirely due to the dynamic pressure, which is just the kinetic energy of the flow. By taking the square root of that pressure difference, you have isolated the exact velocity.
And the most mind-blowing part of this story.
What's that?
We still use this exact 18th century technology today on our most advanced flying machines.
Oh, yes.
If you walk onto the tarmac and look at the nose or the wings of a modern commercial airliner, you will see these little sharp metal probes sticking out, pointing straight forward. Those are Pitot tubes.
Yep.
They are using the exact same energy trading principle Henry de Pitot used in the River Seine to tell the pilots how fast the plane is tearing through the atmosphere.
It's a perfect testament to the universal, unbreakable truth of these conservation laws. Air behaves as a fluid just like water does.
Right.
And Pitot tubes are often used in modern industry alongside another historical invention based on Bernoulli called the Venturi tube.
The Venturi tube.
Invented by Giovanni Battista Venturi. This device measures flow rate not by stopping the fluid, but by deliberately choking it.
Choking it, like the garden hose.
Exactly. It's a pipe with a smoothly narrowed throat in the middle. As we discussed, forcing the fluid through the narrow throat makes it speed up, which makes the static pressure drop.
Right. Higher velocity, lower pressure.
So by installing one pressure sensor in the wide part of the pipe and a second sensor in the narrow throat, you can constantly monitor the pressure drop. From that precise drop in pressure, the system's computer can instantly calculate the exact volumetric flow rate passing through a pipeline.
Okay, I have to step in here and play the role of the stubborn skeptic for a second.
All right, hit me.
I hear what you're saying about energy trading flawlessly back and forth. But if Bernoulli's equation says total energy is perfectly conserved, that it just infinitely trades between pressure, velocity, and height without ever losing a single drop of energy, then why the heck do we need water pumps? Right. If I push water into a massive, perfectly horizontal pipeline in Texas, shouldn't it just flow all the way to New York forever? Why do oil and water pipelines have massive billion-dollar pumping stations built every few miles? Doesn't the fluid eventually just stop?
That is the exact question that completely shatters the illusion of the ideal world we've been operating in for the last 20 minutes.
So it's a lie.
Well, you are absolutely correct. If the universe were perfectly ideal, water would flow through a horizontal pipe forever without any pumps. But in reality, the universe demands a tax on movement.
The tax.
We call this tax head loss, and it is primarily driven by the inescapable reality of friction.
And that transition brings us into our second major phase of understanding today, Module 2, the reality of friction, viscosity, and turbulence.
This is where things get real.
Because ideal fluids are great for doing clean math on university chalkboards, but in the real world, fluids stick.
They really do.
They stick to the solid walls of the pipes, and they stick to themselves. To move from Bernoulli's perfect sandbox to the real world, we have to introduce a completely new character to the story, viscosity.
Viscosity is, in its simplest definition, fluid friction.
Fluid friction, okay.
It's a measure of a fluid's internal resistance to flow and deformation. We all know this intuitively. Honey has incredibly high viscosity. It flows like sludge because its internal molecules desperately cling to each other.
Right.
Water has a relatively low viscosity, so it flows easily. But its viscosity is not zero. And because of this microscopic stickiness, a fascinating phenomenon occurs at the boundaries of any container.
What happens at the boundary?
When water flows through a pipe, the outermost layer of water molecules that are physically touching the steel wall of the pipe get stuck.
Stuck, like glued.
Basically. They latch onto the microscopic roughness of the metal. That outermost layer of fluid does not move at all. Its velocity is zero. We call this the no-slip condition.
This was another mind bender for me when reading the source material. The water physically touching the pipe isn't moving.
Not at all.
But it gets weirder. Because the water has internal viscosity, the layer of water molecules just inside that stationary layer drags against it.
Right.
It's trying to move forward, but the stationary layer is pulling it back, so it moves, but very slowly. Then the next layer inwards drags against that slow layer, moving slightly faster.
Exactly. The viscosity transmits the braking force of the wall deep into the fluid.
Okay.
So instead of a solid, unified plug of water moving all at the exact same speed like a train car, you have a velocity gradient.
A gradient.
The water in the dead center of the pipe is moving the fastest because it is the furthest away from the sticky walls. As you move radially outward from the center toward the edge, the fluid gets slower and slower and slower until it comes to a dead stop at the wall.
Imagine sliding a freshly shuffled deck of cards across a table.
Oh, that's good.
The bottom card sticks to the table, the card above it slides a little bit, the card in the middle slides further, and the top card slides the furthest. You end up with this angled, smeared deck.
That's a perfect physical representation.
To describe this complex, layered sliding mathematically, physicists have said move beyond the simple ideal equations and develop what are known as the Navier-Stokes equations.
Developed independently by Claude Louis Navier in France and George Gabriel Stokes in Ireland during the 19th century. These equations are the absolute bedrock of modern fluid dynamics.
So bedrock.
Essentially, they take Newton's second law of motion force equals mass times acceleration and apply it to a microscopic three-dimensional cube of fluid.
Okay, zooming way in.
They tally up every single conceivable force acting on that tiny fluid cube. The pressure forces pushing on its faces, the body forces like gravity pulling it down, and crucially, the viscous shear forces tearing at its sides.
And just uttering the phrase Navier-Stokes is enough to send a shiver down the spine of any engineering student.
Oh, absolute terrifying.
These are famously considered some of the most difficult, unsolvable equations in all of human mathematics, right? There is literally a $1 million prize out there from the Clay Mathematics Institute for anyone who can prove certain properties of these equations.
They are notoriously impenetrable, yes. And the reason they are so difficult comes down to a mathematical nightmare known as convective acceleration.
Convective acceleration. Okay, break that down for me.
In a standard physics problem, an object's velocity changes over time. But in a fluid, the velocity of the fluid isn't just changing over time, it's changing as the fluid moves through three-dimensional space.
Wait, what?
The fluid's own velocity determines how fast its velocity changes.
To visualize that, imagine a massive traffic jam. The speed of the cars determines the flow of traffic, but the flow of traffic dictates the speed limit of the cars. It's a snake eating its own tail.
That feedback loop creates nonlinear terms in the differential equation.
Nonlinear meaning.
Nonlinear means the variables multiply against themselves. The math doesn't scale up in straight, predictable, proportional lines. A tiny change in one variable can cause an exponentially massive, chaotic change in another.
The butterfly effect kind of thing.
Exactly. Because of this nonlinearity, there are no general analytical solutions to the Navier-Stokes equations. We can't just draw a random shape of a pipe on a piece of paper, plug it into the equation, and get a perfect mathematical answer for how the fluid will behave.
We can only solve them exactly if we aggressively cheat and constrain the physical world.
Pretty much.
For example, if we imagine a steady, slow flow moving between two infinite, perfectly parallel flat plates. In that highly specific, highly unrealistic case, all those nasty, complex, chaotic, nonlinear terms zero out.
And when you simplify it that much, you can prove mathematically that the velocity profile of the fluid forms a perfect, smooth, mathematical parabola. The fastest fluid is exactly in the center, and it curves symmetrically down to zero at the walls.
We call that beautifully smooth, orderly flow, laminar flow.
Laminar flow.
The fluid moves in parallel, microscopic layers, or laminae sliding past each other, without any mixing across the layers.
Right.
In the mid-1800s, a German engineer named Gotthelf Hagen and a French physician named Jean Poiseau independently derived the formulas for this type of flow in cylindrical pipes. They proved that in laminar flow, the pressure drop required to push the fluid is directly, linearly proportional to the velocity.
Nice and simple.
Right. If you want the water to move twice as fast, you just need twice as much pressure. It's a linear, predictable relationship.
But there is a massive catch.
Always a catch.
Laminar flow is incredibly fragile. It only exists at very low speeds, or in very narrow capillary tubes, or with highly viscous fluids like oil. If you take a normal pipe with water and you start turning up the flow rate, the fluid becomes unstable.
To determine exactly when that stability shatters, engineers use a critical metric called the Reynolds number, named after the British physicist Osborne Reynolds.
The Reynolds number.
The Reynolds number is essentially a mathematical tug-of-war. It is a ratio that pits the inertial forces against the viscous forces.
Think of the inertial forces as the raw momentum of the fluid. It's the mass of the water violently trying to plunge straight ahead as fast as possible.
Okay, forward plunging.
The viscous forces, on the other hand, are the stickiness of the fluid, desperately trying to keep all the microscopic layers sliding smoothly and parallel to each other.
When the fluid is moving slowly, the viscous stickiness is strong enough to hold everything together. The Reynolds number is low, and the flow remains smooth and laminar.
Yeah.
But as you crank open the valve, the velocity increases. The brute force forward momentum of the inertial forces starts to overwhelm the delicate, sticky bonds of viscosity.
The Reynolds number climbs.
And once it passes a certain critical threshold, which in a standard round pipe is a Reynolds number of roughly 2320, the orderly layers break down completely and permanently. The flow descends into total chaos. We call this turbulent flow.
Osborne Reynolds actually visualized this beautifully in 1883.
How did he do that?
He set up a clear glass pipe with water flowing through it, and he injected a tiny, needle-thin stream of dark dye into the very center of the flow.
Okay, injecting dye.
When the water was moving slowly, the dye formed a perfectly straight, beautiful, unbroken thread running the entire length of the pipe. It was a perfect visual of laminar flow. The layers weren't mixing.
Right.
But the moment he increased the velocity past that critical Reynolds number, the straight thread of dye instantly shattered. It exploded into a chaotic, swirling cloud, instantly mixing across the entire width of the pipe.
Chaos is absolutely the right word. Reynolds discovered that in turbulent flow, the fluid particles aren't just moving cleanly forward anymore.
No, they're not.
On top of their average forward speed, they are constantly violently fluctuating in every conceivable direction. They are vibrating, swirling, and darting sideways.
Mathematically, physicists started representing the velocity in turbulent flow not as a single number, but as an equation.
Okay, an equation.
The instantaneous velocity, which we call u, is equal to the steady average velocity, u bar, plus a chaotic, constantly changing, fluctuating velocity, u prime. So u equals u bar plus u prime.
And it's those fluctuating velocities, specifically the ones darting laterally sideways across the pipe, that ruin everything.
They really do.
Because of those sideways fluctuations, macroscopic chunks of fluid literally slam into each other. You have incredibly fast-moving groups of molecules from the center of the pipe getting violently thrown outward into the slower-moving layers near the edge.
Yeah.
At the same time, slow-moving chunks from the edge are getting sucked into the fast center.
This violent lateral mixing transfers a massive amount of momentum across the pipe.
It's like imagine two trains running on parallel tracks at different speeds, and passengers are constantly throwing heavy bowling balls back and forth between the trains.
That's a great analogy.
The fast train will be slowed down, and the slow train will be dragged forward. In a fluid, this violent momentum exchange creates a massive new type of internal friction. We call these Reynolds stresses.
And Reynolds stresses create an unbelievable amount of extra drag. This is why pumping water through a turbulent municipal pipeline requires exponentially more electrical energy than if the flow were laminar.
Oh, because of the extra friction.
Right. The pump isn't just fighting the friction of the pipe wall anymore. It has to provide the energy for the fluid to violently fight itself in billions of microscopic swirling eddies.
And trying to calculate the mathematical value of these Reynolds stresses was a massive, seemingly insurmountable roadblock in physics for decades.
A huge roadblock.
The Navier-Stokes equations were too complex to solve for this level of chaos. You couldn't predict the U-prime fluctuations. It seemed like a dead end.
That is, until a man named Ludwig Prandtl came along.
This is genuinely one of my favorite stories in the history of science, because it shows how raw observation can crack impenetrable math.
It's a great story.
Ludwig Prandtl is widely considered the founding father of modern fluid dynamics. He was a professor at Göttingen University in Germany in the early 1920s. And the story goes that he was incredibly frustrated.
Understandably so.
He had been staring at chalkboards, trying to figure out how to mathematically model these chaotic, turbulent fluctuations to calculate the Reynolds stresses. But the math was too abstract. He couldn't find a way to anchor it to reality.
He needed a physical model, a tangible, measurable variable that could describe the size and behavior of these swirling eddies.
Completely burnt out, Prandtl decides to take a walk outdoors to clear his head. He's standing on a balcony or a hill, looking out at the horizon, and he sees an industrial factory in the distance with a tall smokestack.
Okay, a smokestack.
There is a strong breeze blowing, and a massive plume of smoke is trailing horizontally out of the chimney. And he just stops and stares at the swirling, chaotic vortices of smoke tumbling through the sky.
And in that chaotic plume, his genius mind recognized a pattern.
Yes. He realizes that the vortices of smoke, the swirly eddies, are not entirely random in size.
Right.
The eddies swirling down near the solid ground are relatively small and tight. But as he looks higher up into the open sky, further away from the solid boundary of the Earth, the swirling eddies of smoke are massive, expansive, and broad.
He mathematically estimates in his head that the diameter of a swirling vortex is directly, linearly proportional to its physical distance from the solid ground.
Specifically, he theorizes that the vortex size is roughly 0.4 times its distance from the boundary.
It was a monumental epiphany that changed engineering forever.
It really did.
Prandtl rushed back to his chalkboard and applied this visual observation directly to his turbulent pipe flow problem. He theorized that these microscopic turbulent eddies inside a pipe act like distinct parcels of fluid.
Parcels of fluid.
They travel a certain average lateral distance before they crash into another parcel, mix, and transfer their momentum. He called this specific travel distance the mixing length.
And the absolute stroke of genius was realizing that this mixing length isn't a random variable. Just like the factory smoke, the size of the turbulent eddies inside a steel pipe depends entirely on how far away they are from the solid wall.
Exactly.
Right next to the steel wall, there's no room to swirl, so the eddies are tiny. In the dead center of the pipe, far away from the walls, the eddies are massive.
By substituting this mixing length theory, specifically his observation that the mixing length equals 0.4 times the distance from the wall into the complex Reynolds stress equations, Prandtl did the impossible.
He produced a computable algebraic formula for turbulent friction. He managed to tame the mathematical chaos.
Which is incredible.
So if we step back and look at a pipe with turbulent flow, what does the velocity profile actually look like when you graph Prandtl's math? It must look completely different from the smooth, pointy parabola of laminar flow.
It looks fundamentally different because that violent turbulent mixing is so incredibly efficient at transferring high momentum from the fast center out to the slow edges. The velocity profile across the vast majority of the pipe is much flatter.
Flatter.
It's much more uniform. The water across most of the pipe is moving at roughly the same bulk speed. But right against the wall, something deeply strange happens.
Viscous sublayer. This is the ultimate paradox of turbulence.
Precisely. Because of the physical presence of the impenetrable solid wall, those transverse turbulent fluctuations, the U-prime sideways darting motions are physically suppressed.
You cannot have a chaotic eddy swirl straight through a solid steel boundary.
Exactly. So as you get closer and closer to the wall, the mixing length approaches zero, in an unimaginably thin, microscopic layer directly touching the wall. Sometimes only fractions of a millimeter thick turbulence is completely extinguished.
That is wild.
In this tiny zone, called the viscous sublayer, viscous friction rules supreme, and the flow actually behaves as if it were perfectly smooth laminar flow.
It is wild to visualize. You have a pipe full of violently churning, chaotic, turbulent water. But clinging to the inner wall is a microscopic, incredibly slow, sticky skin of perfectly smooth water.
Yes.
And then as you move inward from that skin, the turbulence violently ramps up, creating what Prandtl mathematically derived as a logarithmic velocity curve. The laws of physics completely change depending on whether you are 1 millimeter or 10 millimeters from the steel.
It's amazing to think about all of this complex, invisible architecture happening inside the plumbing, hidden behind our drywall every time we turn on a faucet.
Seriously.
It is a beautifully complex system. But everything we have discussed so far, from Bernoulli's energy trading to Prandtl's mixing length, has assumed one critical thing.
Which is?
We are dealing with closed, pressurized systems, pipes completely full of water. But what happens to the physics when we remove the pressure constraint?
Which brings us to the third phase of our journey, Module 3. Rivers, sewers, and aqueducts.
Yeah.
The mechanics of ion channel flow.
Ripping the roof off.
Exactly. We've looked inside enclosed pipes where water is shoved forward by the pressure of a pump. But what happens when you rip the roof off the pipe? expose the top surface of the water to the open atmospheric air and let gravity take the wheel?
Well, the moment you have a free surface exposed to the open air, the atmospheric pressure pushing down on the water is constant everywhere. Therefore, the internal pressure gradient that was driving the fluid in a pipe drops to zero.
So it can't be pushed by pressure anymore.
Right. A river cannot be pushed by pressure. Instead, open channel flow is driven entirely by gravity. The water flows because it is falling down a slope.
But as we just spent 20 minutes discussing, the fluid was also experiencing viscous friction against the solid bottom and sides of the riverbed or the concrete channel.
Exactly.
So it becomes an eternal tug of war. Gravity is constantly pulling the mass of the water down the incline, trying to accelerate it faster and faster. But the viscous friction and the turbulent eddies dragging along the rough riverbed are pulling backwards, trying to slow it down.
And when a steady state is finally reached in a river or a canal, those two opposing forces achieve perfect equilibrium.
Perfect balance.
The specific component of gravity pulling the water down the geometric slope exactly equals the frictional shearing force of the channel's boundary. When this mathematical balance is achieved, the water flows at a constant, steady depth and a constant, steady velocity. It stops accelerating.
To predict this velocity, civil engineers use empirical equations, the most famous being the Manning equation, or Chazy's formula. And these formulas rely on a really clever, incredibly important geometric concept called the hydraulic mean depth, or hydraulic radius.
The hydraulic mean depth is a ratio.
Okay, how does that work?
You calculate it by taking the total cross-sectional area of the flowing water and dividing it by what we call the wetted perimeter.
The wetted perimeter.
The wetted perimeter is simply the total linear length of the solid channel that is physically touching the water. If you look at a cross-section of a river, it's the length of the riverbed from the left bank down across the bottom and up to the right bank. It represents the total zone of friction.
Let me make sure I understand the implications of this.
Yeah.
If I want water to flow as fast and efficiently as possible down a hill, I want the largest possible area of water pushing forward, but I want the smallest possible wetted perimeter dragging it back.
Exactly.
I want to maximize the flow area while minimizing the friction surface.
That is the exact optimization problem every civil engineer faces when designing a drainage canal or a sewer system. Let's do a mental exercise.
Right.
Imagine you need to design a rectangular concrete channel with exactly 10 square feet of cross-sectional area. You could design it to be 10 feet wide, but only 1 foot deep.
Okay, 10 wide, 1 deep.
In that scenario, the wetted perimeter is 10 feet along the bottom, plus 1 foot on the left wall, plus 1 foot on the right wall. That's 12 total feet of friction surface.
Okay, but what if I redesign it to be 5 feet wide and 2 feet deep? The area is still exactly 10 square feet. But now the wetted perimeter is 5 feet across the bottom, plus 2 feet on the left, plus 2 feet on the right.
Right.
That's only 9 total feet of friction surface. By just changing the geometry, I've eliminated 25% of the frictional drag, even though it's carrying the exact same volume of water.
Yeah.
The narrower, deeper channel will flow much faster.
Exactly. And mathematically, if you take this geometric optimization to its absolute limit, calculus dictates that for any given cross-sectional area, a full circle has the absolute smallest possible perimeter.
Which brings me to one of my favorite historical mind-blowers of all time from our sources, the Roman aqueducts.
Oh, the Romans were geniuses.
Starting around 300 BC with the Aqua Appia, the Romans built these towering stone structures that carried millions of gallons of fresh water over dozens of miles to supply the baths and fountains of Rome. And if you climb to the top of an intact aqueduct today and look at the cross-section of the actual water channel carved into the stone, what shape is it? It's a perfect semicircle.
It is a breathtaking feat of engineering intuition. By carving a semicircular channel, the Roman engineers were unknowingly perfectly optimizing the hydraulic mean depth.
Unknowingly.
A semicircle flowing right to the brim has the mathematical minimum possible wetted perimeter for an open channel exposed to the air. They minimize the frictional drag of the rough stone walls to the absolute theoretical limit, which allowed the maximum possible volume of water to flow.
They built these massive spanning stone structures stretching to the horizon, maintaining an imperceptibly tiny downward slope, sometimes dropping only a few inches over an entire mile, all perfectly optimized for advanced fluid dynamics 2 millennia before the Navier-Stokes equations were ever written down.
It is just staggering to think about.
It really is.
It is a testament to the power of trial, error, and observation. But open channel flow isn't just about steady rivers and ancient, gently sloping plumbing.
What else is there?
Because the top surface of the water is unconstrained and free to move up and down, open channels can exhibit some incredibly dynamic, violent, and unstable behaviors. To understand these extreme behaviors, we have to look at the energy of the flow differently. We use a concept called specific energy.
Okay, let's unpack specific energy.
Right.
How is this different from the total energy we talked about with Daniel Bernoulli and the roller coaster?
It's a subtle but vital shift in perspective. In a closed pipe, we track total energy relative to some arbitrary fixed datum point, like sea level.
Okay.
But in an open channel, the bottom of the channel itself is constantly sloping downward. So specific energy measures the total energy of the fluid relative to the bottom of the channel it is currently flowing over.
Relative to the bottom. Got it.
It's the sum of the water's physical depth, which represents its pressure and potential energy, plus its velocity head, which is its kinetic energy.
So if a river is carrying a constant flow rate of 1,000 gallons per second, it can physically carry that volume in 2 very different ways.
Right.
It could be a very deep, slow-moving, lazy river. That flow has massive depth energy but very little kinetic energy. Or that exact same 1,000 gallons per second could be flowing through a shallow, incredibly fast-moving mountain rapids. That flow has very low depth energy but massive kinetic energy.
Precisely. And if you graph the specific energy required to sustain both of those states, you find that the curve is shaped exactly like a sideways C.
A sideways C, okay.
And right at the vertex, the absolute leftmost tip of that C curve, there's a minimum point. There is one specific mathematically derived critical depth, where the specific energy required to push that exact flow rate is at its absolute minimum.
This critical depth isn't just a math trivia fact. It acts as a massive physical boundary line in nature.
It does. If the water is flowing deeper than this critical depth, it is moving relatively slowly and peacefully. We call this a tranquil or subcritical flow. But if the water is shallower than the critical depth, it is moving violently fast. We call this a rapid or supercritical flow. The laws of fluid behavior completely invert depending on which side of this boundary you are on.
And we have a neat mathematical tool to determine which side of the boundary we're on, right? The Froude number.
Yes, named after William Froude, a 19th century naval architect. The Froude number is a dimensionless ratio.
What does it compare?
It compares the actual forward flow velocity of the river to the speed at which a shallow surface wave naturally travels through that same depth of water.
Like a ripple.
Right. If you drop a heavy pebble into a still pond, ripples spread outward in perfect circles. Those ripples have a strict mathematical speed limit dictated by gravity and the depth of the water.
Let me see if I can visualize the implications of this. In a tranquil, subcritical flow, like a deep, lazy river, the bulk velocity of the water is slower than the natural speed of a ripple. The Froude number is less than 1. This means if I throw a rock into that tranquil river, the ripples can actually travel upstream, fighting against the current, because the wave is moving faster than the river itself.
Exactly.
The river can feel obstacles ahead of it because the pressure waves travel upstream to warn the water.
That is a perfect visualization. But now consider a rapid, supercritical flow, a shallow, violently fast mountain stream rushing over rocks.
Okay, supercritical.
In this state, the bulk water is moving much faster than the natural wave speed. The Froude number is greater than 1.
Wow.
If you throw a rock into a supercritical rapids, the ripples cannot travel upstream. They try, but the sheer speed of the river sweeps them downstream faster than they can propagate.
That's fascinating.
The water is moving entirely blind. It cannot send pressure waves upstream to warn the incoming fluid about an obstacle.
Wait a minute. Moving faster than your own waves? Unable to send pressure signals ahead of you. That is exactly how a supersonic fighter jet works.
Yes.
The jet is flying faster than the speed of its own sound waves. In a supercritical rapid flow, the water is literally supersonic relative to its own wave speed.
The analogy is mathematically and physically flawless. Tranquil flow is subsonic. Rapid flow is supersonic.
It's just get good.
And just as a fighter jet decelerating from supersonic to subsonic speeds creates a violent, explosive shock wave, a sonic boom water transitioning from rapid to tranquil flow does something equally dramatic, violent, and visible.
What does it do?
It creates a hydraulic jump.
A hydraulic jump. This is where the chalkboard math suddenly explodes into massive real-world destruction. Rapid flow is inherently unstable.
I mean, it's stable.
If you have a super fast, shallow layer of water racing down a steep concrete incline, and then the incline suddenly flattens out, the water cannot sustain that rapid supersonic state.
Right.
It violently rear-ends the slower, deeper, tranquil water ahead of it, and it explosively shifts states.
It literally jumps. The surface of the water abruptly, near vertically rises, churning into a massive, frothing, stationary wave of extreme turbulence. A tremendous amount of kinetic energy is violently dissipated as heat and deafening noise as the fast water violently crashes into the slow water.
And civil engineers use this explosive phenomenon intentionally.
They do.
Think about the spillway of a massive structure like the Hoover Dam. When the reservoir gets too high, they release water down that massive, steeply angled concrete slide. It drops hundreds of feet, building up terrifying speed.
It is a highly supercritical, extremely rapid flow, moving at highway speeds.
If that water were allowed to just blast into the natural dirt riverbed at the bottom at 100 miles per hour, the sheer kinetic energy would scour the earth.
Oh, it would.
It would erode the foundational bedrock of the dam itself, potentially causing the entire multi-billion-dollar structure to collapse within hours.
It would be catastrophic. So to prevent this, at the very bottom of the spillway, engineers design a massive concrete basin called a stilling basin, often with a slight upward ramp.
And what does that do?
They deliberately mathematically trigger a hydraulic jump. They force that rapid supersonic water to crash into a deep wall of tranquil water, creating a massive, churning, boiling standing wave the size of a building.
They use the hydraulic jump to act as a giant liquid brake.
Yes.
It dissipates all of that destructive kinetic energy safely within the heavily armored concrete basin, tumbling over itself. So by the time the water exits the basin and continues down the Colorado River, it has returned to a slow, safe, tranquil flow.
It is the aquatic equivalent of harnessing an acoustic shockwave to protect our infrastructure. It's a perfect manipulation of energy states.
That is just incredible.
Which provides the ideal pivot point for our final transition. So far, we have looked at fluids moving around solid boundaries inside pipes and down concrete channels. But for our final phase, we need to completely invert our perspective.
Phase 4, Module 4, flying, driving, and slicing. Instead of a fluid flowing through a stationary pipe, what happens when a solid object violently forces its way through a stationary fluid?
Yeah.
This is the realm of external aerodynamics. We are talking about the aerodynamic drag on your car when you hit 70 on the highway, the lift generated by a Boeing 737 wing, and the immense forces crushing a submarine.
When an object forces its way through a fluid, it experiences a mechanical force resisting its motion. We broadly call this drag. But just as we learned that fluid friction is complex inside a pipe, drag on an external body is not a single, simple phenomenon. It is fundamentally split into two wildly different types.
Right.
Friction drag and form drag.
Okay, friction drag makes intuitive sense based on what we've talked about with viscosity and the no-slip condition.
Right.
This is simply the fluid physically rubbing against the skin of the object. It's the viscous shear stress trying to grab the surface. If you have a long, thin, flat plate slicing edge first through the air, perfectly parallel to the wind, almost 100% of the drag it experiences is friction drag. The air is just grabbing at the microscopic roughness of the metal sides.
Exactly. But form drag, which is also commonly known as pressure drag, is entirely different, and it is the dominant force on blunt objects, like a cylinder, a sphere, a golf ball, or the flat grill of a semi-truck.
Blunt objects.
And to truly understand why form drag exists, we have to revisit our ideal world one last time, to look at a hilarious historical math fail known as D'Alembert's paradox.
I love the history of scientists just getting utterly baffled by their own math.
It's pretty funny.
So in the 1750s, a brilliant French mathematician named Jean-Laurent D'Alembert applies Euler's ideal, perfectly frictionless fluid equations to calculate the drag on a simple cylinder placed in a flowing stream of water. The math says that the fluid hits the dead center front of the cylinder, creating a high-pressure stagnation point. Then the fluid smoothly divides, flowing perfectly around the curved sides, speeding up and dropping in pressure.
Because of Bernoulli, right.
Exactly. And finally, because the fluid is perfectly ideal, it flows perfectly back together at the exact rear of the cylinder, slowing down and seamlessly regaining all of its original high pressure.
And because the flow is perfectly symmetrical front to back in an ideal fluid, The high pressure pushing backward on the front of the cylinder is exactly mathematically canceled out by the equally high pressure pushing forward on the back of the cylinder,
resulting in D'Alembert publishing a paper concluding that a solid cylinder experiences absolutely zero drag.
Zero drag.
You could theoretically throw a baseball in this ideal fluid, and it would glide forward forever without ever slowing down, which of course is completely absurd and contrary to literally all human experience of walking against the wind or throwing a rock into a pond.
He was so confused.
D'Alembert himself was totally baffled. He reportedly said that the theory of fluids was an illusion.
The paradox remained a humiliating stain on fluid dynamics for over a century until our old friend Ludwig Prandtl finally solved it with his boundary layer theory.
Prandtl again.
Yes, the fatal flaw was ignoring viscosity. In the real world, a thin, viscous, slow-moving boundary layer forms on the surface of the cylinder due to the no-slip condition.
Here's where the physics gets intense. As the fluid travels past the widest, thickest part of the cylinder and tries to negotiate the curved rear half to close the gap, it has a massive problem.
A huge problem.
According to Bernoulli, the pressure at the wide sides is very low, but the pressure at the rear stagnation point is supposed to be very high. So the fluid flowing around the back half has to flow from a low-pressure zone into a high-pressure zone.
It has to flow against what we call an adverse pressure gradient.
They're trying to flow uphill in terms of pressure. It's like trying to push a car up a steep hill.
Exactly. Now, the fast-moving fluid far away from the cylinder has plenty of kinetic momentum to push through this high-pressure hill and close the gap.
Right.
But the fluid trapped deep inside the microscopic boundary layer has already lost a massive amount of its kinetic energy due to the viscous friction rubbing against the cylinder's surface.
It's exhausted.
It simply doesn't have enough momentum left to push uphill against the adverse pressure gradient all the way to the back.
So the boundary layer fluid literally stalls out. It stops moving forward. The high pressure behind it actually pushes it in reverse, and the flow completely rips away from the surface of the cylinder.
We call this catastrophic failure flow separation.
Flow separation.
And when the flow separates, it cannot smoothly close back in around the rear of the object. Instead, it creates a massive, chaotic, churning wake of swirling, turbulent eddies behind the cylinder. Because the fluid never smoothly regains its pressure, the pressure inside this chaotic wake remains very, very low.
Now look at the balance of forces on the object. You have high stagnation pressure violently slamming into the front grille of the cylinder, but you have a low-pressure vacuum of chaotic eddies sitting directly behind the cylinder.
The pressure is completely lopsided.
That massive difference in pressure literally sucks the object backward. That suction is form drag.
And this explains the entire basis of aerodynamic design. It's why modern sports cars, airplane wings, and submarine hulls are shaped like teardrops.
Teardrops, right.
A long, gently tapering, streamlined rear end gently guides the high-speed air back together, dramatically reducing the steepness of the adverse pressure gradient.
So the boundary layer can make it.
Exactly. This allows the exhausted boundary layer to make it all the way to the end, delaying or entirely preventing flow separation. No flow separation means no low-pressure wake, which means practically zero form drag. Streamlining is simply the art of tricking the air into gently closing the gap behind you.
But completely blunt objects like a telephone pole or a round power line can't trick the air. They're going to suffer massive flow separation.
They absolutely will.
And the low-pressure wake they leave behind is not just a random fuzzy jumble of air. As the wind speed, the Reynolds number, increases past a certain point, the swirling eddies in the wake begin to organize themselves into an incredibly beautiful, mathematically precise alternating pattern.
Yes, the Kármán vortex street, named after Theodor von Kármán, another legendary 20th century fluid dynamicist.
The Kármán vortex street.
Instead of a continuous, messy blur of turbulence, the cylinder starts shedding distinct, massive, individual vortices. One vortex spins off the top edge, creating a low-pressure zone pulling the wire up.
What?
Then a moment later, a vortex spins off the bottom edge, pulling the wire down. Then the top, then the bottom, over and over, trailing behind the object downwind like a staggering, perfectly spaced line of alternating whirlpools.
This vortex shedding is incredibly regular and rhythmic. Engineers can even predict the exact frequency, how many times per second these vortices will shed, using a dimensionless metric called the Strohhole number.
The Strohhole number.
And this alternating rhythmic shedding exerts a violent, cyclical, oscillating physical force on the object itself. It yanks the object up, then down, then up, then down, like a rapidly plucked guitar string.
And that leads to one of the most poetic phenomena in physics.
Yes. Here's where it gets really interesting. This exact phenomenon of alternating vortex shedding is what causes telephone and power lines to sing or hum on cold, windy, wintry days.
It's such a haunting sound.
The wind blows across the perfectly cylindrical wire, and as the Kármán vortices shed alternately from the top and bottom at hundreds of times per second, they violently vibrate the heavy wire.
Yeah.
The eerie singing tone you hear isn't the wind itself. It is the audible acoustic frequency of the Strohel number vibrating the metal wire. It is literally fluid mechanics making music. It's the same principle behind the ancient Aeolian harp, an instrument played entirely by the wind.
It is beautiful, but vortex shedding isn't always so benign.
Really? When is it bad?
If the frequency of the shedding, the Strohel number, happens to perfectly match the natural structural resonant frequency of the object it's hitting, it can cause catastrophic oscillations.
Oh, resonance. Like shattering a glass.
Precisely. The alternating low-pressure zones will literally tear a tall steel chimney or suspension bridge apart, violently shaking it until the metal yields.
Okay, so we've exhaustively covered drag. The force is pushing you backward and shaking you apart. Now let's talk about the holy grail of aerodynamics. The force pulling you upward against gravity. Lift.
Well, fun stuff.
How exactly does a multi-ton Boeing 777 wing work? How do hundreds of tons of metal and luggage manage to float in the thin sky?
To understand lift, you need a specific fluid ingredient that drag doesn't inherently require.
What's that?
Circulation. To generate a sustained lifting force, you must induce a rotary spinning motion in the fluid around the object.
The spin.
If you take a uniform, straight horizontal flow of wind and mathematically superimpose a circulating flow of air spinning in a circle around the object, something magical happens to the velocity profile.
Let's visualize this. On the top of the object, the circulating spinning flow is moving in the exact same direction as the uniform headwind.
Exactly.
The two velocities add together, making the air rushing over the top move incredibly fast. But on the bottom of the object, the circulating flow is spinning forward, fighting against the uniform headwind.
Right.
They subtract from each other, making the air on the bottom move much slower.
And because of our deep dive into Module 1, we know exactly what happens next.
Bernoulli's equation.
Exactly right. High velocity on the top means very low static pressure. Low velocity on the bottom means much higher static pressure.
The high pressure on the bottom literally pushes the object upward, trying to fill the low pressure void on the top.
That net upward pressure difference is lift. We calculate the exact magnitude of this force using the Kuta-Joukowski theorem, which proves mathematically that lift is directly proportional to the density of the air, the velocity of the airplane, and the strength of that invisible circulation.
And this principle isn't just for heavy airplanes. It absolutely dictates the physics of modern sports.
Oh, everywhere in sports.
Think about a pitcher throwing a devastating curveball in baseball. When the pitcher violently snaps their wrist upon release, they put a massive, rapid spin on the ball.
The baseball is a simple sphere, but because of the viscosity of the air, and specifically the raised, rough red cotton seams on the leather gripping that air, the spinning ball violently drags a microscopic layer of air around with it as it flies.
It physically creates its own circulation.
Yes.
So if a pitcher throws a fastball with extreme topspin, the top of the ball is spinning forward directly into the oncoming air. It slows the air down, creating high pressure on top.
Okay.
The bottom of the ball is spinning backward with the air, speeding it up and creating low pressure on the bottom. The high pressure on top physically pushes the ball down toward the earth faster than gravity alone.
Which is terrifying for a batter.
A 95-mile-per-hour fastball with extreme topspin will suddenly, sharply drop an extra foot right as the batter swings over it. It's called the Magnus effect.
It's the exact same aerodynamic reason a tennis player uses extreme backspin slice to make a ball float seemingly endlessly over the net.
Oh, right.
Or why a skilled soccer player can bend a free kick laterally around a solid wall of defenders into the corner of the goal. They are using viscosity to weaponize Bernoulli's equation.
Weaponizing Bernoulli. I like that.
But perhaps the most incredible, counterintuitive manipulation of fluid dynamics in all of sports has to be the golf ball.
The dimples.
Yeah.
Every kid wonders why golf balls aren't perfectly smooth. A smooth, shiny sphere seems like it should be more aerodynamic.
It seems like it, yeah.
But if a professional golfer hits a perfectly smooth ball with a driver, it will only fly about half as far as a standard dimpled one. It will literally fall out of the sky.
This brings us perfectly full circle back to form drag, adverse pressure gradients, and flow separation.
How so?
Well, a golf ball is a blunt, spherical object. As it flies through the air at high speed, the The flow naturally wants to separate very early on the curvature of the ball, creating a massive, turbulent, low-pressure wake that violently sucks the ball backward, killing its forward momentum.
So how do dimples help?
The hundreds of tiny dimples carved into the surface act as microscopic vortex generators.
They intentionally trip the delicate boundary layer. They force the smooth, fragile laminar boundary layer to immediately transition into a chaotic, turbulent boundary layer.
Exactly. And to a layman, it seems completely counterintuitive. Why on earth would you intentionally create turbulence on the surface of a projectile?
Yeah, that sounds bad.
Because, as we learned with Prandtl, a turbulent boundary layer involves massive lateral mixing. It is constantly pulling high-speed, high-kinetic energy air from further out and violently mixing it down right next to the surface of the ball.
Oh, wow.
That extra injected energy allows the boundary layer to fight against the adverse pressure gradient much, much longer. It has the strength to cling to the curved surface of the ball much further around the backside before it finally, inevitably stalls and separates.
The dimples delay the flow separation. By making the high-energy air cling longer, the physical size of the low-pressure wake behind the ball is drastically reduced. The backward suction of the form drag plummets.
It's a brilliant, highly calculated engineering trade-off.
You willingly accept a tiny bit more friction drag from the rough, dimpled surface rubbing the air in exchange for a massive, game-changing reduction in form drag. The ball effortlessly slices through the air and flies twice as far.
It is arguably the most elegant fluid engineering in consumer sports. Now, obviously, a massive commercial aircraft wing does not spin like a baseball to create circulation, and it isn't covered in golf ball dimples.
No, it is not.
So how does a rigid, stationary wing generate that required circulation to fly? They achieve it entirely through their highly specific asymmetrical geometry.
The aerofoil shape. A wing has a thick, rounded leading edge at the front, but a very, very sharp, tapering trailing edge at the back.
That razor-sharp trailing edge is the absolute key to flight.
Why is it so sharp?
When an airplane powers up its engines and starts to accelerate down the runway, the air initially tries to flow symmetrically, wrapping all the way around the back of the wing from bottom to top.
Okay.
But the air simply cannot negotiate that incredibly sharp hairpin turn at the trailing edge at high speed. The flow violently separates there, and the viscosity of the air rips off a tight, violently spinning eddy of air called a starting vortex.
A starting vortex.
This vortex is literally left behind, spinning on the runway tarmac as the plane accelerates away.
But the universe and the laws of physics demand balance. According to Joukowsky's hypothesis regarding the conservation of angular momentum, if a vortex spins clockwise in the fluid, an equal and opposite counterclockwise circulation must be created somewhere else to maintain zero net angular momentum in the total system.
Right, you can't just create spin out of nowhere. Precisely. When the wing violently sheds that starting vortex off the back, an invisible, theoretical bound vortex of equal strength is mathematically and physically locked around the wing itself, spinning in the exact opposite direction.
And that spinning is what we need for lift.
Yes. This bound vortex provides the massive circulation needed to make the air over the top of the wing move much faster, and the air under the bottom move slower. The pressure drops on top, the pressure spikes in the bottom, and lift is born. The plane leaves the ground.
But wings have hard physical limits. If a pilot gets too aggressive, pulls back on the yoke, and tilts the nose of the plane up too high, increasing what we call the angle of attack, they are forcing the air to work too hard to climb the steep slope of the upper wing.
Very true.
Just like the flow separating behind the blunt cylinder, the boundary layer on top of the wing runs out of kinetic energy trying to climb that massive adverse pressure gradient, and it violently rips away from the metal.
The flow separates entirely. The smooth, high-speed clinging air that was creating the massive low-pressure suction on top of the wing instantaneously collapses into a chaotic, churning, useless wake of turbulence.
And then what?
Lift drops to near zero in a fraction of a second, and drag spikes massively. This catastrophic event is called an aerodynamic stall.
A stall?
If a heavy commercial plane stalls at a low altitude, it simply stops being a flying machine and becomes a falling rock. The physical angle of the wing has pushed the fluid dynamics past its absolute breaking point.
And speaking of pushing fluids past their physical breaking point, we absolutely cannot end this deep dive without returning to the destructive hook we started the show with.
Ah, the ship propellers.
Right. We touched on how air stalls, but what happens when liquid water itself breaks down?
This raises a profound question about the absolute limits of Bernoulli's equation.
How so?
We established early on that as fluid velocity increases, static pressure decreases. But water has a hard physical limit on how low its internal pressure can possibly go before its molecular bonds fail. That limit is its vapor pressure, the precise pressure at which liquid water physically boils and turns into a gas.
Normally, we boil water by putting a pot on a stove and heating it up to 100 degrees Celsius. We raise the internal energy of the water until it can overcome the heavy atmospheric pressure pushing down on it from the air.
That's the normal way.
But you can also boil water at room temperature without adding a single degree of heat, simply by removing the pressure pushing down on it.
And that is exactly what high-speed underwater machinery accidentally does. Let's return to the massive steel propeller of a cargo ship, or the impeller inside a high-power industrial water pump.
Okay, the propeller.
The blades of a propeller are essentially just spinning hydrofoil wings. They create lift, which in a nautical context we call forward thrust, by moving water extremely fast over their highly curved metal surfaces.
If the captain throttles the engines and the propeller spins fast enough, the velocity of the water rushing over the curved back of the blade becomes so incredibly high that, following Bernoulli's law, the local static pressure drops drastically. If it spins fast enough, the pressure drops below the ambient vapor pressure of water. The water doesn't just flow over the blade anymore. The liquid water literally rips apart and boils at ocean temperature right on the surface of the spinning metal blade.
It instantaneously flashes into millions of tiny, localized vapor bubbles, or cavities, hence the name cavitation.
Cavitation.
But these vapor bubbles are incredibly short-lived. The propeller is spinning rapidly, violently sweeping these low-pressure bubbles out of the ultra-low pressure zone on the curve of the blade and shoving them backward into the surrounding normal, high-pressure ocean water.
And when a microscopic, ultra-low pressure vapor bubble is suddenly surrounded by heavy, crushing, high-pressure water, it doesn't just gently pop like a soap bubble in the air.
No, it does not.
It collapses, implosively, violently.
The surrounding high-pressure water rushes inward from all sides simultaneously to fill the void left by the collapsing vapor. The walls of water violently crash into themselves at the absolute dead center of the bubble at supersonic speeds.
Supersonic implosion.
This microscopic supersonic implosion generates an intense acoustic shockwave, along with a microscopic high-speed jet of water that shoots out from the center of the collapse.
A shock wave that can reach localized pressures of up to 200 atmospheres. That is roughly 3,000 pounds per square inch of force. It's like a microscopic stick of dynamite going off.
Exactly.
And if that bubble happens to collapse while it's physically touching or even just hovering millimeters away from the solid metal blade of the propeller,
the supersonic jet of water and the acoustic shock wave act like an infinitesimally sharp, incredibly powerful microscopic drill. It strikes the metal with such unfathomable force that it instantly microfractures the surface of the steel.
Wow.
A single bubble does microscopic damage, but over hours, days, and months, millions upon millions of these supersonic bubble collapses will literally eat away solid steel, bronze, or titanium.
Which explains the pitted, scarred propellers we talked about at the beginning.
They leave deep, jagged pockmarks that look exactly like severe acid burns, completely destroying the heavy machinery and eventually causing the propeller to snap.
Mechanical engineers have to spend thousands of hours designing entire complex systems, massive municipal water pumps, hydroelectric dam turbines, high-speed submarine hulls, specifically to calculate and strictly avoid hitting that critical cavitation threshold.
Because fluid dynamics at that extreme is no longer just moving water. It is literally a destructive force that annihilates solid metal.
It is the ultimate, humbling testament to the hidden, awe-inspiring power of fluids. We started this hour by looking at a simple garden hose, imagining an ideal, perfectly behaved, frictionless stream of mathematical energy trading.
We've come a long way.
And we end by visualizing microscopic acoustic shock waves, chewing their way through thick, solid steel in the depths of the ocean.
It's quite the journey.
Class dismissed. What an unbelievable paradigm-shifting journey today. We have literally unpacked the invisible architecture of the physical world.
We really covered a lot of ground.
We saw how Daniel Bernoulli's concept of energy trading gives us the high-speed Pitot tubes on commercial airliners. We walked with Ludwig Prandtl as he watched factory chimney smoke and mathematically tamed the impossible chaos of turbulent friction.
Incredible minds.
We saw how brilliant Roman engineers unknowingly optimized the hydraulic mean depth of their spanning aqueducts, and how modern dam builders harness the violent supersonic shock of a hydraulic jump to protect our vital infrastructure.
Yeah.
We learned why wintry power lines sing their straw old number, why golf balls rely on dimpled turbulence to fight form drag, and why spinning propellers can literally boil the ocean and tear themselves apart.
The mental toolkit is complete. You now have the fundamental lens required to see the invisible mechanics behind the motion of the world.
I certainly do.
But before we sign off, I want to leave you with one final, deeply personal thought to mull over. We've spent this entire deep dive talking about massive industrial pipes, rushing rivers, commercial airplanes, and ocean freighters. But consider the fluid dynamics happening inside your own body at this exact second.
That is a wild pivot. Where are you going with this?
Well, your heart is a biological pump, right?
Right.
Tirelessly cycling roughly 2,000 gallons of fluid every single day.
Okay.
But it isn't pumping ideal frictionless water. It is pumping blood. A highly viscous, non-Newtonian fluid densely packed with red cells, white cells, and complex proteins.
That's true.
And it is pumping it through a massive, sprawling, branching network of flexible, living pipes that constantly expand and contract with pressure.
Okay, I see where you're going.
How do the microscopic boundary layers and viscous shear stresses we discussed behave when the pipe itself is actively pulsing? How do the shear stresses of viscous friction affect the delicate cellular inner lining of your arteries over a lifetime?
Wow.
How do Bernoulli's principles of narrowing vessels, pressure drops, and velocity spikes dictate the long-term health of your vascular system every time your heart beats, every single second of your life? The laws of fluid dynamics aren't just out there in the industrial world. They are the very mechanical laws keeping you alive right now.
That is absolutely something to think about the next time you feel your pulse racing. If you haven't already, give us a like and follow, and please leave us a comment if you enjoy the podcast. We'd love to hear from the folks who make this possible.